We'll have to look at that. Okay, so, and actually I'm going to bring up, I showed you a periodic table online called, what is it? P table. So like if you just Google P table, it'll show you this periodic table. Interactive periodic table I want to show you. But out there is all sorts of sources that you could actually find the answer to how our electrons configured around an atom of that sort of element. It's all out there. And there are definitely exceptions. And I want to talk you through why the exceptions occur, starting with chromium. That's where the first exception occurs. Now, you won't need to show me how electrons are configured as they are exceptions to the lowest n plus L rule, but you need to kind of understand why they occur. Okay, so chromium. What's up with chromium? Well, chromium is atomic number 24, so we need to find homes for 24 electrons. Using the arrow diagram, okay, this is how they would be configured. Okay, this is in the order of filling, and this must be in the order of increasing n. Okay, so remember that whenever we say in order of filling, that's probably how you load the electrons according to the arrow diagram. And in order of increasing n, that's where you kind of unscramble them. So in this case, we basically moved the 4s out. The electrons, 24 electrons, look the same. So the thing is, that's how you would answer it on a test, but this is really what chromium does. So let's kind of look at how this is different than what we would expect. So if you focus on these last, the electrons in the last two orbitals, the 3d4 and the 4s2, 6 electrons, right? So what's different is actually, instead of 2 electrons going in the 4s, one of those electrons basically jumps ship and goes to, however you want to say it, jumps ship and goes to a higher energy. That's what it does. You're like, why would it do that? The answer actually lies on the next slide. If you think of what a D, any D, you could call it 3D if you wanted to, what any D subshell looks like. It has 1, 2, 3, 4, 5. It has 5 orbitals. And that's why this exception has occurred. So it can actually half fill the D subshell. That's it. Okay, so exceptions to the lowest n plus L rule do occur. You're not going to be coming up with them on a test. Apparently you had some in your homework. But the reason they occur has to do with either half-filled, like we saw with chromium. So the half-filled chromium 3D subshell went 3D5. Okay, it's a 3D4, 4s2. A full-filled D subshell, a half-filled F-type subshell would be F7, or a full-filled F-type subshell. So that's where these exceptions occur. So yeah, I'm going to actually show you question number 78 dealt with that element right there, which is the element molybdenum. So these are all by atomic number. Chromium is atomic number 24. The next one, atomic number 29, etc. So it's okay however you answered 78. So this is number 78. Apparently I'll have to kind of carefully grade those with some slack, okay, for other times. But this is molybdenum. It's hard for me to say that word today. Maybe always. But this actually is problem number 78. And now with that in mind, if you were going to come up with the homes for those 42 electrons around a molybdenum atom, you would base them on krypton, because molybdenum is in period number 5. I'm getting better at it. So the rare gas in period number 4 is Kr. So we do brackets Kr. Beyond krypton, looks like we need to find homes for 1, 2, 3. So this is how you use this. Beyond krypton, we need to find homes for 1, 2, 3, 4, 5, 6 electrons. We would say that we would go 5s2, because this is the s block, and this is period 5, and then we'd go 1, 2, 3, 4. And this actually is D block, so I need 4 electrons in the D block. Remember, this is n minus 1, so instead of 5, it's actually 4D. So that's how that works, in case you're wanting to kind of use a periodic table to kind of bounce around to come up with electron configurations. So that, anyway, that's how you would say molybdenum is configured, the electrons, the 42 electrons around a molybdenum atom. And you would get it totally right on my test. But like you see up here, and like we saw with chromium, one of those electrons jumps ship, okay? And so actually the real deal is more like Kr 5s1 4d5, which actually is right there. Okay? So that's how that works. All right. So one last little thing I want to talk about with regard to electron configuration is actually this. In the next part, which we are going to get to today, although we aren't going to get to another homework assignment, in the next part we're going to talk about compounds. And the cool thing about compounds is basically atoms are chemically bonded together. The thing that bonds atoms together, for instance, we pick on water a lot. A water molecule, you know, you have your oxygen, chemical bond hydrogen, chemical bond hydrogen. So those chemical bonds between the central oxygen atom and the 2 hydrogen atoms, it's all about electrons. Okay? And specifically, when atoms bond together to make a chemical bond, like with that water molecule, they are either going to lose electrons, gain electrons, and create an ionic bond, or electrons are going to be shared and are going to create a different type of chemical bond called a covalent bond. Okay? But whatever they do, whether they lose or gain electrons or share electrons, it's all about getting this, what we call rare gas configuration for their valence electrons. Now, some of you guys have learned this as a complete octet, but I will draw your attention to if you take the 2 electrons in the NS subshell and the 6 electrons in the NP subshell, actually you do get 8. This is sometimes called a complete octet. More about this in the next part. So, valence electrons. Valence electrons actually collectively make up the valence shell of an atom. So valence electrons always have the highest N. So remember we've talked about N. N is that principal energy level. So for instance in 4s, you know, the value of N is 4. You know, in 3p, okay, the value of N is 3. Okay, so the highest N, actually, once you come up with how the electrons are configured, those are your valence electrons, and collectively they make your valence shell. So let's look again at potassium, and this is like unscrambled in order of increasing N. So here finally is why would you ever take a perfectly good electron configuration and unscramble it? This is why. Because it emphasizes the highest N. So it's not always the last added. The highest N is not always the last added, but the highest N are your valence electrons. So the highest N we have here is N is equal to 5. Okay, so we have 2 electrons, 2 valence electrons making up its valence shell for potassium. Another one we did earlier was iodine. If you take all of its electrons and show how its subshells are in increasing N, okay, in this case, actually, again, you get the highest N value of 5, okay, but notice here, we've got actually 7 valence electrons. So the 2 electrons in the 5s and the 5 electrons in the 5p collectively make the valence shell for a neutral iodine atom. All right, so valence electrons, big hairy deal. So valence electrons, how do you know how many valence electrons an atom has? And actually, it works out pretty good for the main group elements. And I'll remind you, because earlier we talked about the periodic table, how to chunk it up. And main group elements are group A. Okay, so what are the group A? Well, you have the first two columns, you skip the B, because those are the transitions and the inner transitions, and then you go to the last 6 columns. Those are your group A elements. So you know the number of valence electrons, okay, just by its group number. Now an exception is helium, because I don't think it's an exception. Okay. So I brought in a periodic table to show you that. So we picked on 2 elements a minute ago. We picked on potassium. Okay. So potassium is a group 1A element, so it has 1 valence electron. It did have 1 valence electron. And then we went and picked on iodine. Okay, iodine is a group 7A, final answer. Did we pick on iodine? 7A element, and so it has 7 valence electrons. Okay. All right. So the last one that you need to do is 84. So this actually will be due, I think you'll be fine with this. This actually will be due on Wednesday. Not a whole lot to it now. In this case, it basically says all of these arrows are valence electrons. Okay? So right away, you know you have 4 valence electrons, you know 5 valence electrons, etc. So right away, you know what group it's in. Okay? Then also it goes ahead and it tells you, you know what periods it's in because of the 3s. These are all in period number 3. Shouldn't be too bad. But then it says what element is it, and it asks if these electrons look to you like they would be hanging out in their ground state. We talked a lot about how electrons load. So for instance, the first one doesn't look like it. No ground state to me. Okay? So that's kind of how that goes. Second one, still no ground state. It's a subtle thing, but but it still means you can still answer which atom they belong to, those numbers of valence electrons. Okay, on to compounds. Oh, so we are going to skip part 3 again this semester, but come back to it on atomic size. Hope you're okay with that. So skip ahead a little bit. The reason is we kind of need to get down the road a little bit. This week's lab, I am pleased to announce that there is no, I don't think there, you said there's no pre-lab either?
There's no calculation.
Yeah, there is a pre-lab for nomenclature. So there is no lab, there's no calculations. But what I will do, and you will earn lab credit, ka-ching, is I will give you a take-home, basically a take-home assignment after we do nomenclature that will be due, let's not wait till, I'll have to decide whether it's due Monday or the following Thursday. It won't be due Friday. Okay, so that's kind of what we'll do. Actually, 2 labs. That's called a dry lab. So we're going to talk about nomenclature this week, this Thursday, and the next Thursday is another dry lab. We're going to do Lewis structures. So we have 2 labs, no lab write-ups, and I'll do the same thing for Lewis structures, what I'm going to do for nomenclature. I'll give you an assignment, you do it, and come turn it back for home for lab credit. Ka-ching!
Yeah, you get to build dot structures.
Yes.
Do you get to build them again with the little blocks? Because that was super fun.
That's yeah. Cameron took Introduction to General Chemistry with me, so we kind of have an overlap for a few things. So that's one of them. Okay, let's talk about those chemical bonds. So a compound is something you're probably already familiar with. Basically, you have to have 2 or more atoms that are chemically bonded together in a unit, okay, that you know kind of the relative amounts of the atoms of each type of element that are going to be bonded together. in definite proportions. I have a video. My videos worked. This is actually trying to I know we've talked about compounds before.